Chapter 7, Unit 5. Let's talk about inferential statistics. Inferential statistics use sample data to make inferences about a population. There will be error involved because a sample, again, is not a perfect representation of a population. Researchers must decide how much error they are willing to accept. For the following example, we're going to use 5% as our acceptable error rate. In statistical terms, this is called an alpha level. This means that the alpha level would be equal to 5%, and we would write this as alpha equals 0.05. This means that we recognize 95% of scores as being close to the mean. So here's an example. Let's suppose that a psychologist is planning a research study to evaluate the effect of a new growth hormone. It is known that regular adult rats with no hormone weigh an average of 400 grams with a standard deviation of 20. The psychologist plans to select a sample of 25 newborn rats, inject them with a growth hormone, and then measure their weights when they become adults. Let's say that this sample mean is 410 grams for those 25 rats. Are the rats with the growth hormone noticeably different from the regular population of rats? Well, step 1, we know that the population of the rats' weights is normal, so we have a normal distribution. And the expected value of the mean for the sample would be 400 because the population mean is 400. Step 2, let's go ahead and calculate the standard error. For this sample, we would find a standard error equal to 20 over the square root of 25, which would give us 4. Using 95% at the middle of the distribution, this leaves 5% for the tails. Notice that there are two tails. So if 95% is in the middle, that leaves 2.5% for each tail. This translates to a p-value in the tail of 0.0250. So if you look in the tail column on your table and find the value closest to 0.0250, you'll find z equals 1.96. From the graph, we know that we have both positive and a negative 1.96. The other way to do this would be to put a line straight down the middle of the graph and use column D in the table by dividing the 95% into two separate parts. Step 3, make the table using your z-scores and the x values using the mean of 400 and your standard error of 4. Okay, place lines at the z-scores of plus and minus 1.96. And then let's determine what the sample means are for each of these cutoff lines that we put on our graph. So given the equation, m is equal to mu plus z times standard error, fill in what you know. So for the left line, you use negative 1.96, and you get a sample mean of 392.16. For the right line, you get a mean of 407.84. And this fits perfectly within our graph, within our x values. It matches well. So the conclusion, we have determined that a sample of 25 untreated rats with no growth hormone is almost guaranteed with a 95% probability to have a mean between 392.16 and 407.84. At the same time, it is very unlikely, a probability of 5% or less, that a sample mean would be in the tails beyond these two boundaries without the help of a real treatment effect. So for this problem, the sample mean we were given was 410 grams, and this is outside those two boundaries. It's located in one of the tails, which is also known as the rejection region. Therefore, we do have evidence that the growth hormone does have an effect. These rats' weight is very, very different from the other 95%, which are in the middle of the distribution. So here's a learning check. See if you can do it. Pause the video. A sample is obtained from a population with a mean of 100 and a standard deviation of 20. Which of the following samples would produce a z-score closest to 0? So we have to calculate z-scores for all four problems. First step would be to calculate a sample mean, then calculate a z-score. Check your work with mine, see if you got the same answers, and then to decide what the final answer would be, the closest to 0 would be the smallest z-score. So it would be A with a z-score of 0.50. Learning check problem 2. For a normal population with the mean of 80 and standard deviation of 20, which of the following samples is least likely to be obtained? So again, you're going to do your work for each of these four problems. You're going to find a z-score, and the z-score that's least likely to be obtained is one that's in the extreme. So the larger the number of the z-score. So let's calculate that. So let's look at the work for each sample. So again, we want to find the one that's least likely to be obtained. So that's the one that's the furthest away to the highest z-score. That would be C with a z-score of 2. Learning check problem 3. For a normal population with a mean of 100 and a standard deviation of 15, which of the following would be the most extreme and underrepresentative? Again, the most extreme is the same as problem 2. It's the one with the highest z-score. So let's calculate z-scores for every single one. Remember, the sign doesn't matter. What matters is the number. The biggest number is the one that's farthest away from the mean. So in this case, for C, I found a z-score of -3.33. That would be my